Welcome to the Deep Dive, part of the AI Paper Podcast series. We plunge into the latest research to bring you the most impactful insights, fast. Today, we're tackling, a really central problem in modern AI. This insatiable appetite large language models have for high-quality data. It's a huge challenge for anyone in our field because getting good human-generated data is just so costly, it's scarce, and let's be honest, it's often got biases and errors baked in. How do we feed these incredible machines effectively when, the traditional ways just hit so many walls, especially as these models keep getting bigger?
Yeah, exactly. And that's precisely what this paper tackles. It's called CoT-Self-Instruct, building high-quality synthetic prompts for reasoning and non-reasoning tasks. It's by Ping Yu and colleagues from FAIR at Meta and NYU, and it proposes this really quite clever solution, basically having LLMs generate their own high-quality training data. Think of it like teaching an AI to teach itself, but, and this is key, with a strategic twist to make sure that data is actually top-notch.
Okay, so let's do the quick version first for our short-form edit. This deep dive focuses on CoT-Self-Instruct. It's this groundbreaking method that lets LLMs not just generate synthetic data, but do it using strategic chain of thought, or CoT reasoning. And then, this is the really cool part, it automatically filters that data for quality, making sure every piece is genuinely valuable.
Right. The key insight here is that by combining this LLM-driven planning with really rigorous self-curation, the synthetic data it generates, it actually significantly outperforms existing human-curated datasets, and it beats standard self-instruction methods too. It's kind of a paradigm shift for data generation. We're seeing better performance with less human effort, fewer raw samples needed. It changes the whole cost-benefit calculation for LLM data, quality over sheer quantity, basically.
And these aren't just like theoretical gains, right? We're talking tangible improvements. We're seeing better scores on really critical reasoning benchmarks, things like MAP 500, AMC 23, ANIME 24, GPQA Diamond. Plus, superior results on non-reasoning tasks too, like instruction following measured by AlphaKeyval 2.0 and Arena Hard.
Yeah, essentially, this work offers a powerful shortcut. It helps you get well-informed about how to build more capable LLMs much faster. It shows a viable path to high-quality data without those usual human bottlenecks that, have kind of plagued the field. It pushes us closer to maybe more autonomous AI development.
So our mission for this deep dive is crystal clear. We're going to unpack exactly how CoT-Self-Instruct gets these impressive results, and crucially, what it means for the future of LLM training, especially for those of you listening who are actually building or working with these models, trying to stay ahead of the curve. Okay, let's start with the core problem LLMs face. We all know LLMs are changing deep learning, but their development just absolutely hinges on massive amounts of high-quality data. Why is getting that data such a persistent headache for researchers and engineers?
Well, it's a really tough knot to untie. Getting human data is just incredibly challenging, often totally impractical at the scale needed for today's huge models. It's expensive, obviously. Data scarcity is a real thing in specialized domains. And then you have privacy concerns, right? Curated and others pointed this out back in 2023. And beyond that, research from people like Hoskins, Singh, Ghilardi, they all highlight that human data just inherently comes with biases and errors, which, isn't ideal if you want to train robust and fair models. It's like demand for perfect data way outstrips the supply.
Right. So synthetic data emerged as this really promising alternative, a way to maybe bypass those human constraints. And a foundational step there was the original self-instruct method from Wang and colleagues in 2022.
Right.
That's where LLMs basically started generating their own instruction following examples from just a small set of seed samples, kind of bootstrapping their own learning process.
Precisely. And since then, we've seen various attempts to improve on that. Some tried to increase query complexity, like Liu et al. In 23 and Zheng et al. In 24. Others focused on semantic diversity, like Ding et al. 23, or just scaling up the data, like Yuan et al. 23. And there were even self-improvement loops from Yuan et al. Just this year. But despite all these efforts, a really significant challenge remained. How do you ensure the quality and the actual effectiveness of that generated data for training? Like, it's one thing to generate tons of data, but it's quite another to generate genuinely useful data that makes the model better. And that's exactly where CoT-Self-Instruct comes in.
Okay, so with these big data challenges kind of hanging over everything, how does CoT-Self-Instruct actually do what it promises? What's its unique approach to cracking that quality problem, especially across different kinds of tasks, from simple instructions to really complex reasoning?
Yeah, that's the key distinction. CoT-Self-Instruct is, it's ingeniously designed with two really distinct stages. First, there's synthetic instruction creation with chain of thought. And second, there's synthetic instruction curation, which is basically a robust automated filtering process. So it's not just generating, it's generating smartly and then validating what it generated. So in stage 1, that synthetic instruction creation with CoT, it all starts with a small pool of human annotated seed instructions, like the original Self-Instruct. But here's the crucial difference, and it's a big one. CoT-Self-Instruct first tells the LLM to carefully analyze those seed instructions. It makes the LLM look at their domain, their complexity, their purpose. It's sort of like a pre-computation step, if you like.
Interesting. So it's almost like the LLM is doing some kind of metacognition there, thinking about how to make a good prompt before it actually makes it.
Yeah.
That sounds incredibly useful for quality.
That's a great way to put it, yeah. The LLM then reasons step by step, using chain of thought, to come up with a plan. A plan for generating a new, self-contained instruction that explicitly matches the quality and complexity of those seeds it analyzed. And only after that planning phase, where it's basically outlined its approach, does it output the final synthetic instruction. And it does so in a very strict, predefined format. It's a deliberate, structured thinking process before it, writes anything down.
Can you give us a practical example? Like, what does this look like for different task types? I can picture it for a math problem maybe, but what about more open-ended stuff?
Sure, so for verifiable reasoning tasks, think math, logic puzzles, where there's a definite right answer, the LLM is instructed to generate both the instruction and its verifiable target answer. So for instance, it might generate a math problem like, find the value of k such that the system of equations kx plus y plus x plus k equals $1 has infinitely many solutions. And then it also provides the answer, maybe formatted like boxed dot. This whole process ensures the answer is baked into the generation template. It's derived as part of the reasoning, not just guessed afterwards. You can see this in figure 2 in the paper. Now, for general instruction following tasks, things with more open-ended responses, like writing a story or explaining a concept, the LLM generates only the instruction. But to avoid weird, unnatural prompt combinations, like asking it to mix storytelling and coding in the same prompt, which would be kind of jarring, the seed prompts are first categorized into domains, things like writing and storytelling, technical and programming, creative and design, and others. This lets the system sample seeds only from the same category when generating a new prompt. It keeps the generated content coherent and genuinely useful for specific types of tasks. That's shown nicely in figure 3.
Okay, that planning stage sounds really thorough. But even with all that, I imagine not every single instruction it pumps out is going to be perfect, right? What's the strategy for quality control? How do they ensure the data is truly usable? Because, even smart LLMs can generate nonsense sometimes.
You're absolutely right. And that's where stage 2, the curation step, becomes critical. Even with powerful LLMs doing careful CoT planning, some generated instructions might still be ill-defined, maybe ambiguous, or just plain unanswerable in a helpful way. So for those verifiable reasoning tasks, they introduce something pretty neat called answer consistency. Here's how it works. The LLM generates multiple responses, let's say K responses, to its own generated instruction. It then looks for the majority vote among those responses. Now, if this majority response doesn't match the target answer that CoT-Self-Instruct generated back in stage 1, the one derived with all that careful reasoning, then that whole data example instruction and answer gets rejected, thrown out. This gives an extra layer of filtering, and the paper shows it's actually superior to standard self-consistency filtering because it leverages that pre-computed, reasoned-out correct answer. It's like a strict internal fact checker saying, hold on, do the solutions actually lead back to the known answer?
That sounds incredibly robust, almost like a double check. Does it catch pretty much everything, or are there still edge cases?
Well, no system's perfect, especially with really tricky logical paradoxes or extremely complex reasoning. But answer consistency significantly cuts down on errors. It adds that critical self-verification against a known target derived from reasoning. It's a huge leap from just checking if multiple attempts agree with each other without knowing the real answer. Okay, now for the non-verifiable instruction following tasks where there isn't one single correct answer, like creative writing or open-ended questions. Here, they use the rejecting instruction preferences, or RIP method. This was actually developed by Yu et al. More recently in 2025. So again, the LLM generates K responses to the instruction. But this time, each response is evaluated by a reward model. A reward model is basically another LLM that's been trained to judge how good, how helpful, how aligned a response is. The filtering decision is then based on the distribution of these reward scores. They select prompts that consistently lead to responses getting high scores from the reward model. You can kind of picture it like figure 1 in their paper shows. If a prompt's responses consistently get top marks, it's deemed high quality and kept for training. If the scores are all over the place or consistently low, it gets rejected.
So the LLM isn't just generating the data, it's also acting as its own pretty sophisticated quality control department, constantly checking and refining. Is that the gist? Like a self-improving loop?
Exactly. It's essentially a closed-loop system. The LLM is both the creative engine generating the material and the meticulous editor ensuring its quality. This intrinsic quality control built right into the pipeline is a massive reason why CoT-Self-Instruct really stands out from earlier methods.
Right, but theory is one thing. The proof, as they say, is in the pudding. All this clever methodology sounds great on paper, but what actually happened when they put CoT-Self-Instruct to the test in experiments? Did it really move the needle on model performance?
It absolutely did. And the paper details extensive experiments across both reasoning and non-reasoning domains. The results are frankly pretty compelling. They really highlight the practical impact this could have for anyone building these kinds of models. So for reasoning tasks, they used the Qwen 3-4B base model, and they trained it with GRPO, that stands for General Reinforcement Learning from Rule-Based Verifiable Rewards. It's basically a way to fine-tune models using clear, objective feedback on whether an answer is correct or not, especially useful for math and logic. And they evaluated it on really standard, challenging benchmarks: Math 500, AIM 2024, AMC 23, and GPQ-A Diamond. These are well-respected tests of mathematical and general reasoning ability. Okay, get this. Even without any filtering applied, just the raw output from the CoT-Self-Instruct generation process, the data achieved an average accuracy of 53.0% on these benchmarks. That clearly outperformed data generated by the standard self-instruct method, which only managed 49.5%. So a noticeable jump right from the start, before any curation.
Wow. And what happened when they applied the filtering? Did that boost things further, even though it meant technically throwing out some data? That seems a bit counterintuitive if you just want volume.
It made a significant difference. Applying filtering boosted performance for both methods, actually, even though it did reduce the total number of training examples. And this really hammers home a crucial point for anyone working in ML today. It's not just about the sheer volume of data anymore. It's about getting high-quality synthetic data. That's what truly moves the performance needle, even if you end up using fewer examples overall. And CoT-Self-Instruct consistently kept its edge. For example, with that answer consistency filtering we talked about, it hit 57.2% average accuracy. Compare that to standard self-instruct using self-consistency filtering, which got 53.6%. Still an improvement over no filtering, but not as good as CoT-Self-Instruct with its specialized filtering. You can see this in Table 1, and here's maybe the most impressive part. CoT-Self-Instruct generated prompts, once filtered, vastly outperformed existing human annotated datasets. Take S1K, which is a diverse set of human instructions often used for benchmarking, that only got the model to 44.6%. Or Open Math Reasoning, a dataset focused specifically on math problems, 47.5%. CoT-Self-Instruct beat both, even when using fewer training samples. For instance, using just about 2,900 filtered CoT-Self-Instructions led to that 57.2% average accuracy, way higher than S1K's 44.6%, using almost 900 prompts. And when they scaled up the CoT-Self-Instruction data with answer consistency filtering to 10,000 samples, the accuracy climbed even higher to 58.7%. This really could change how people approach data acquisition for these tasks. Okay, now for the non-verifiable instruction following tasks. Here they use the Llama 3.1-8B instruct model. They train it using DPO, direct preference optimization, which is a popular method for fine-tuning models directly on preference data, basically teaching them to produce responses humans prefer. And they evaluated using Apache Eval 2.0 and Arena Hard, using powerful models like GPT-4 Turbo and GPT-4o as judges to score the quality of the responses. And again, CoT-Self-Instruct came out on top. It achieved an average score of 53.9% compared to standard self-instruct's 47.4%, and this is before applying any filtering. What's particularly interesting here is they also found that prompting the generator LLM to produce longer chain of thought reasoning chains during the initial planning stage led to even greater gains in the final model's performance. This really highlights a cool insight. The quality of the thinking process within the LLM while it's generating the data seems directly correlated with how good the final trained model becomes. It's not just about the output data, but how the LLM arrived at generating that data. That initial planning really pays off downstream.
That makes sense. And for these open-ended tasks where you don't have a single right answer, how much did that RAP filtering help? Did it manage to pick out the genuinely better, more preferred instructions?
Absolutely. Applying the RIP filter boosted CoT-Self-Instruct's results from that 53.9% up to 54.7%. Now, RIP filtering also improved standard self-instruct, but CoT-Self-Instruct still maintained its lead. And what's more, CoT-Self-Instruct with RIP filtering significantly outperformed training on actual human prompts taken from the WildChat dataset, that's a well-known dataset of human chatbot conversations. Training on WildChat prompts got a score of 46.8% without filtering, and only 50.7% even with RIP filtering applied. So this clearly shows that synthetic data, when it's generated intelligently like this and curated rigorously, can actually surpass the performance you get from training on real human interactions. They even pushed it further by exploring online DPO training, where the model learns continuously from preferences. In that setup, CoT-Self-Instruct combined with RIP reached a really impressive 67.1% average score compared to training on the human prompts, which plateaued at 63.1%. So yeah, the evidence across the board is pretty clear. CoT-Self-Instruct produces superior results, showing a really promising path forward for training highly capable LLMs much more efficiently.
Wow. Okay, so stepping back, this deep dive into CoT-Self-Instruct really makes you think, doesn't it? It feels like a powerful leap in how we can train these models. We're sort of approaching a new frontier here.
It truly does signify a crucial shift, I think. LLMs are becoming, well, more autonomous in their own development pipeline by using chain of thought for smarter data generation and then meticulously curating that data with methods like answer consistency and RIP filtering. CoT-Self-Instruct effectively tackles that data bottleneck. And the result is models that are just demonstrably more capable both at complex reasoning and at following nuanced instructions.
Yeah, this feels like a profound development for anyone building or working with LLMs. It really pushes the boundaries of what you can achieve with self-generated data. Maybe the days of solely relying on massive, expensive human data sets are perhaps numbered for certain applications.
Indeed. And this research naturally raises a really important question for all of us to consider looking forward. As LLMs get better and better at generating and refining their own high-quality training data, how is the role of human data likely to evolve? Will humans mainly become curators, the ones providing those initial high-quality seed prompts? Or could we see entirely synthetic, self-improving data pipelines becoming the standard way to build the next generation of AI? Definitely something to chew on as you think about the future of your own projects and the field in general.